All right. Welcome, everyone. Hopefully you're in the right place. We're here for SEC341. We're going to talk about reducing costs and operational overhead by building an enterprise-scale PKI on AWS. And today I'm joined by Anthony Scheller. I'll let him introduce himself in a second here. But I'm Zach Miller. I'm a Principal Security SA for Amazon Web Services. I'm based in Chicago. I've been with Amazon about 5 years. Tony, go ahead.
Hi, I'm Anthony Scheller. I'm currently the head of security engineering at StubHub and based out of Santa Monica, Southern California, if you guys know where that is. Yeah.
Okay, so what are we going to talk about today? Today I want to go over, kind of the basics first. What is AWS Certificate Manager, ACM? What is AWS Private CA? Tony and I will level set a little bit. Hopefully most of you are familiar with PKI concepts, but Tony and I are going to talk about what is the CA hierarchy, what is revocation, some of these basics, just so everyone's kind of on the same page. Tony will get into StubHub's journey with PKI on AWS, why they rebuilt their PKI on AWS, pun intended, what their objectives were and what the solution ended up being. And most importantly, I think, what were some of the lessons learned that they had after they went through this process? And hopefully, how can you learn from those lessons too? And then we'll also talk a little bit about some recommended practices. I also have a spiel about AWS's vision for how AWS Private CA will operate, and kind of these connectors that we're building to try to facilitate a bunch of different use cases, like Active Directory certificates and certificates for mobile devices with SCEP, or Simple Certificate Enrollment Protocol. So we'll talk a little bit about those connectors, and then I'll just wrap up with what are some best practices for operating a PKI in general, but in particular using AWS Private CA. Just before we get started though, can I see a raise of hands, who's an engineer? Whose role is an engineer? Okay, awesome. What about compliance officer or something related to compliance? One or two people. Anyone in a non-technical role, like a project manager or something? Okay, awesome. And who's already familiar with PKI to some extent? Okay, most people. Okay, good. We'll try to keep the basic stuff to a minimum then. Okay. So let's talk Private CA, or really about certificates in general. There are two certificate services on AWS that you want to be aware of. One is AWS Certificate Manager, or ACM. The other is AWS Private CA. ACM is primarily for public and private TLS certificates, and it's really only supposed to be used with, or meant to be used with, integrated services like Application Load Balancer, API Gateway, CloudFront. There are many others, but those are probably the three most common ones. And so what we built the service was to allow you to, again, kind of issue certificates, whether public or private, and bind them to these resources, and we can help with renewal, right? So ACM has this concept of managed renewal, where when that certificate is up for renewal, it will just automatically issue a new certificate and bind it to that resource. So like an ALB, for example. And obviously you can see the value in that. You don't need to go and manually keep track of renewals, manually. When I was more of a system admin, I did a lot of certificate stuff, and I found that I was pretty constantly logging into Linux servers and manually putting a certificate into a key store, and it's a pain. It's difficult to manage. You could mistype something and make mistakes, and frankly, when I was in that role, I said I'm never ever going to work with certificates again, and now it's all I talk about every single day at AWS. So I don't know. I don't know how that happened, but basically ACM is nice for taking out some of that operational heavy lifting and kind of letting ACM or AWS manage that for you. And I mentioned public certs just to call this out. The public certs from ACM are issued by what's called Amazon Trust Services. It is our CA hierarchy, or kind of our public CA that we manage as Amazon. Secondly, we have AWS Private CA. AWS Private CA is a fully managed certificate authority service. You can create CAs, manage those CAs, all without having to manage hardware security modules or HSMs. You're not really managing the hardware or the servers at all. You just kind of create CAs, and you can make API calls to issue certs, basically. And these are only private certs, I should also say. So to dive deeper into ACM, if you look over here on the screen on the left-hand side, you can import certificates to ACM. So if you get certificates from an external CA or another CA like DigiCert or Sectigo or one of these, you can import those certificates to ACM. The benefit that you get from not importing is managed renewal. Imported certs, we can't do that managed renewal, but certificates that you issue directly from ACM or Amazon Trust Services, we can handle managed renewal on those integrated services like ALB. So you request these public certs, and again, you can associate them with things like CloudFront distro or an API gateway. And you can also issue private certs, and those private certs come from private CA on the back end. So you can create CAs in private CA and then issue private certs from it using ACM. And you might ask, like, why would you do that? You would do that because it enables managed renewal. It enables you to bind those certificates to like an ALB that you wouldn't typically be able to do, right? Like you can't just log into an ALB and put a certificate on it. It's a managed service. So you use ACM to do that. And many customers will use private certificates for other use cases that aren't for services that are integrated with ACM. Like Tony's going to talk about Kubernetes and how StubHub built a PKI to facilitate, at least at some level, certificate issuance to Kubernetes containers. And so many customers have different use cases, and for that you can just directly call our APIs to issue certs. We have these connectors for other use cases that I'm going to talk about later. And so there's a number of ways to kind of get those certs from private CA or ACM. And just, again, diving a little bit deeper into that, like I mentioned, you can get those private certs directly from ACM, but you can also call our APIs and get certificates for IoT devices, VPN, service mesh. These are private certificates. They're highly customizable, so you can make them have any validity period you want. It can be for a bunch of different use cases like code signing or email encryption. There's a lot more flexibility and customization in private certs with private CA, whereas with ACM, you really can only issue TLS certs, and they have a lifetime of 13 months. So if you have these use cases around, hey, I need a code signing cert, or I need a private TLS cert, but it has to live for 3 years or 90 days, you can issue certs from private CA and kind of customize them however you'd like. Okay, so I'm going to pass over to Tony. He's going to talk a little bit about CA hierarchies, what are they, and some best practices.
Awesome, thanks. So yeah, let's first talk about what a CA hierarchy actually is, right? So a certificate authority hierarchy is effectively an inverted tree structure, right, that is used to manage trust in digital certificates, right? And so at the top here, right, you can see we have the root certificate authority. It in itself is the most trusted, right, certificate authority within your hierarchy. And its main job, right, is to, is to only sign other certificate authorities, right? There may be specific use cases where you might want to add or might want to mint certificates directly from the root certificate authority, but in almost all cases, that's definitely not a good idea. And that's really due to two main reasons, right? One of which is, cryptographic blast radius, right? So though you don't have to worry about this too much in AWS, if your, private key for your root certificate authority was exfiltrated or mismanaged somehow, right? Any certificate that you minted from that root certificate authority is then subject to man-in-the-middle attacks and other nefarious stuff that you definitely don't want. The other reason, right, is that if you are using your root certificate authority to sign end entity certificates, the architecture in which you would have to create, right, in order to expose your root certificate authority to the entities that are requesting the certificates just inherently increases the blast radius. Right? And so generally not a good idea, but like I said, there are some very specific use cases where you might want to do that. So next we have, right, the intermediate certificate authority layer. It's aptly named, right? It serves as a cryptographic intermediary, right, between your root certificate authority and your issuing certificate authorities. And really its job, right, is to further compartmentalize, right, the blast radius when it comes to additional certificates, right? And if you think about what we talked about earlier, right, with the root certificate authority, in worst case scenario, right, your private key gets, exfiltrated from the CA or mishandled, right? The only certificates that would be theoretically exposed are the ones that kind of originate from that branch, right? And so, intermediate CAs, right, like I mentioned, it's, also used to sign other CAs or issuing certificate authorities. Then as we're going down the tree structure here, right, issuing certificate authority is really used, right, to issue the, end entity certificates that, you might put on a load balancer or, a server, right? So let's talk about some best practices, right, while we're here. So in AWS and in general, right, you generally want to keep your root certificate authority offline or as, far away from as possible from, the rest of the network and identity and access management blast radius, right? So in AWS, right, you want to keep your root certificate authority in its own AWS account. Then you also want to employ things, right, like certificate revocation, right? So using things like, OCSP, the Online Certificate Status Protocol, which is more of a synchronous revocation kind of situation, or CRLs, which are the certificate revocation lists. And Zach is going to get into all the fun stuff with that in a little bit. And so, yeah, so let's move on here. So let's talk about cross-account CA sharing, right? And as a way to avoid lots of overhead and the cost of managing individual certificate authorities, right? So if you need to be extremely highly available, right, and you want to have your points of presence of your certificate authorities in a bunch of different accounts, right? Normally without this particular feature of cross-account sharing, right, you would have to literally create new certificate authority instances in all of those AWS accounts. And so if we're talking about, cost per CA and level of overhead, right, I think it's like what, 400? Yeah, about 400 per instance of certificate authority or private certificate authority. And so, this kind of helps you not only with complexity, but also with cost, right? And so by show of hands here, who here knows about AWS Resource Access Manager? Okay, a few of you guys. All right, so for those of you who don't know, right, AWS Resource Access Manager is a service, managed service by AWS, and allows you to share certain resources across cloud account boundaries. You could do this in a couple different ways. Specifically, you could use AWS Cloud Account IDs, right? So the actual ID of the account number, or you could actually share it with AWS organizational units, right? It's a mouthful, and we'll get into why this is kind of important for scalability later on. But yeah, so right here we have a reference architecture that kind of illustrates, right, what cross-account certificate authority sharing looks like in practice. So, as we talked about, best practice is having your root certificate authority off on its own, AWS account and disabled and all that good stuff. And so then you have your, issuing certificate authority in the middle here and the security account. And this can be, issuing CAs, or it could be the issuing CAs or other intermediate, whatever your flavor of hierarchy ends up being. And then you can use, right, the AWS Resource Access Manager to share that specific issuing certificate authority out to those two accounts on the sides here. And so instead of having to create actual instances, right, in each one of those accounts, you can actually share it across account boundaries. So I think we'd be remiss if we didn't talk about, resilience, right? So AWS Private Certificate Authority is highly available within a single region, right? But if you're, anything like StubHub and you need to be, highly available at all times, right? Generally, having a single point of failure is definitely not an option. So you might want regional points of presence, right? And so you could really achieve this in two different manners, right? One of which is having, a single root certificate authority, and again, it's a regional construct, right? So a single root certificate authority, and then you have, your issuing certificate authority or subordinate CAs in the same region. That are signed, of course, by the root, and then you could also have, issuing CAs in additional regions that are also signed by that same root, right? And so the pros of this, right, is you can have a single root certificate authority in order to, that you have to manage, right? So when it comes to clients being able to verify TLS, you only have one certificate, CA certificate that you need to worry about and install in your client trust stores. But the con of this, right, is that you don't have full redundant PKI across regions, right? Because you're still sharing that same root. Most cases, this is usually good enough, but just to call it out, right? You can also go into a fully redundant kind of architecture where you have, right, your root certificate authority and respective intermediates and your issuing CAs in one region, and you can do the same, the full same architecture in another region. Pro of that, right, is you're fully redundant across regions. The con of that, right, like you may be guessing, is that you have more certificate or CA certificates to manage and install on your clients, right? So, but yeah, so now I'll pass it back over to Zach and we'll talk about revocation.
Thanks, Tony. One other thing I would say too on the resilience piece is just that, from my perspective, I think having the one root CA in one region makes more sense to me, because what you'll find is, what you only really ever want to use that root CA to sign other CAs, like Tony said, and so when you have one in one region, if there's an outage in the region for your root CA, how likely is it really that you're going to urgently need to sign another CA, like an intermediate CA, in that time while there's an outage? I've never seen a customer run into that, so I think that from my perspective at least, I think the single root CA makes more sense because less management on your side, and again, like unless you have use cases where you really need to mint new CAs urgently, and I've not seen that. Usually it's something you plan months in advance and can easily be delayed if there's an issue. So I would just keep that in mind. But the 2 root CAs can absolutely work too, and there may be use cases for that. As far as revocation, so like why would you want to revoke a certificate? Revocation is when certificates have a natural lifetime, right? A natural validity period. So say you issue a certificate in January of this year, 2025, and it is going to live for 12 months. So in around January next year in 2026, you would want to reissue that cert and bind it to the new resource, right? What happens if in March that certificate private key is exposed somehow? Developer accidentally puts it on GitHub or Pastebin or something, right? Or there may be other reasons why you would want to revoke a cert, but for whatever reason you have a certificate that you want to invalidate before it would naturally expire, essentially. And that's when you would revoke that certificate. And in private CA, or that's really an API call. You make a revoke cert API call to private CA, and clients need to have a way of checking whether a certificate is revoked or not, right? And there are 2 common mechanisms for this. One is CRIL or CRL, Certificate Revocation List. I'm going to call it a CRIL. There's also OCSP, Online Certificate Status Protocol. And really the kind of differences here are CRIL is a static list of revoked certs, right? So when you make that API call to update the cert, it'll be added to this list. In private CA, we store in S3. And TLS clients, when they want to check the revocation status, will there's a field in the certificate that says basically here's where you find the CRIL, the URL. And it'll go download that CRIL, look through the list and see for the certificate serial number I have, is this certificate revoked or not? Is it on this list? If it is on the list, it's revoked and the client shouldn't trust it. If it's not on the list, it's okay and it'll trust it, right? Online Certificate Status Protocol, or OCSP, is a more live kind of query response type mechanism, right? More dynamic. The client makes a request to an OCSP responder, an endpoint, and says, here's my certificate serial number, is it good or not? And you'll get a response that says, yes, it's good, no, it's bad, aka it's revoked, or unknown, I don't know. Why you might use one or the other is CRIL is better for legacy clients, generally speaking, it's older, but also for things like IoT sensors or like sometimes mobile phones, even though they tend to have a lot of memory these days. Especially like an IoT sensor where you have low bandwidth, low memory, it doesn't really make sense to download this big file. Like if you have millions or thousands of revoked certs, it's going to be a pretty large file. So downloading that file and processing it is maybe not going to work for all types of clients. Also, clients typically cache CRILs for about 24 hours. So you might also have this period where you have like kind of a stale CRIL and a certificate's been revoked, but your client still trusts it because it's, it hasn't re-downloaded that cache CRIL. So there are a couple reasons why you might choose OCSP over CRIL in that case. But let's get into like a little bit deeper into what a CRIL workflow looks like. How do clients actually use these? So number one, you say you revoke the cert. So you make an API call. Private CA is going to update that list of certificates in S3. And then when the client wants to say like establish a TLS connection, it will go download that CRIL from that S3 bucket. Again, it finds that location in the actual certificate details in the cert. It'll look through that CRIL and again see like, is this in the list of revoked certs? If not, I'll trust it. And again, you have these kind of limitations around, is it being downloaded by a client that doesn't have very high memory or very low or has like very low bandwidth. And so those are cases like IoT where CRIL probably doesn't make sense. But if you look at OCSP, again, it's very much a more real-time understanding of whether these certificates are revoked or not. You query an endpoint and it responds back, yes, this is revoked, or no, it's not. They are also digitally signed, so you can validate like, is this actually a valid OCSP responder that I'm talking to, which is nice. And it is more memory efficient, like I said. I think some of the trade-offs here are, at least with private CA, it is a paid service where CRIL comes at no additional cost. And you do have to be online, right? So if you have clients that are maybe not online for long periods of time or something like that, OCSP may not make much sense here. And I think one of the other things I didn't mention earlier, but is useful to know, is that you can actually combine both. Like what a lot of customers do is use OCSP and CRIL, and most clients will check OCSP first, and if they can't reach the responder, they'll go and try to download the CRIL or check the CRIL they already have if they've already downloaded it. So if we look at the TLS client workflow for something like OCSP, again, you revoke the cert. That's always step one. We, in this case, instead of updating the CRIL, Private CA will update those OCSP responders and say, hey, this is revoke cert. Here's the serial number. The client will request the certificate to start TLS, and then again, we'll query the OCSP responder. And similar to CRIL, you can find in the certificate details, here's where you find these responders, the URL, basically. So to query these responders, in this case, we actually front the OCSP responders with CloudFront for better, faster delivery to certain locations, geolocations. And so we cache those in CloudFront, but if it is not in the cache, we'll actually go back to the OCSP responder and say, hey, for this given serial number, is this a revoked cert or not? And the responders know, yes, it is revoked in this case, and they will send that, or first cache it in CloudFront and then send that response back to the client so they know it's been revoked and not to trust that cert. And the nice part about caching in CloudFront is then again, if the client or a different client even tries to request information about that same cert, it'll be cached in CloudFront and we'll get a faster response to you. Okay, that's revocation. I'm going to pass back over to Tony. He's going to talk about StubHub and their PKI journey on AWS.
Cool. Thanks, Zach. All right, so let's, for those of you who don't know, let's do a brief intro to StubHub, right? So StubHub is it's a marketplace for individuals and partners to buy and resell live event tickets. We've been around for over 20 years as a leader in the peer-to-peer market exchange industry. Operate two different brands. One is more, prevalent within the US and the other is more international, but StubHub and Viagogo. And so we provide that best-in-class, ticket exchange, in over 90 countries worldwide. So just to give you an idea of the scale, right, that we're dealing with, right? So, so why did StubHub, right, rebuild our own PKI? And so, so there's a couple different reasons, right? So StubHub chose to kind of modernize its platform as a whole, right? A couple different reasons, one of which is to increase developer productivity. The other is to kind of further mature its overall security posture, right? And so in addition to that, right, we also were planning to move fully into AWS. And so during that time, right, we took the opportunity, since we were starting from scratch, right, to kind of rethink all of our cloud fundamentals, right? So that's cloud account architecture and environment structure, networking, identity and access management, logging, edge security, the whole thing, right? Even PKI. And so as it relates to PKI, right, and we were moving into AWS, we really wanted to take advantage of the native integrations that AWS provides, specifically around certificate management and rotation. So things like AWS Certificate Manager, right? And being able to leverage that on the services and the integrations that we already plan on using, such as load balancers, CloudFront distributions, API gateways, and so on. And so our existing PKI at that time just didn't really take advantage of all that. So we chose to kind of re-architect it. In addition to that, right, our previous PKI was not built to kind of, it was not built in the way that satisfied our new cloud account environment architecture, right? So we really wanted to ensure that our internal PKI, the new one that we were going to build, right, actually kind of mapped directly to our new environments, like production and QA, dev, and so on. And so because of that, right, we weren't actually going to be able to use that that existing PKI for one of our cornerstone projects, right, in this modernization time, which was leveraging SPIRE for workload identity. And so this is just another reason why I kind of re-architect this whole thing. So lastly, our previous PKI, right, really didn't meet our new needs when it came to access control. Right, we wanted to ensure that only the entities that could request certificates from our PKI could, and nobody else, as well as the logging and monitoring kind of requirements that we have. Right? We didn't have any of that ability as well, and so. So going on here, right? So you heard me talk for a second about workload identity, right? And what is that, right? So workload identity refers to the mechanism by which you are giving an individual workload a cryptographic identity that it can then use to authenticate to other services, right? So when I say other services, I mean it could be, other in-house services. It could be to cloud service providers. It could be APIs, right? Whatever you want. But the real goal behind this, right, is to be able to facilitate the principle of least privilege. Now, you could argue there's definitely a lot of other benefits to using workload identities, but for the purposes of this conversation and StubHub's use cases, right, it was really about principle of least privilege. And so one of the mechanisms by which we can, distribute those cryptographic identities to those workloads is a open source service called SPIRE. So have you guys, anybody heard of SPIFFE or SPIRE? Okay, a couple of you. Awesome. So as some of you guys already know, right, SPIRE is an open source system for securely managing and distributing those cryptographic identities to individual workloads, right? And so the benefit of, one of the other benefits of having a workload identity is that way those single workloads don't have to share identities across a boundary larger than the actual, than what's needed, right? So if you think about, an identity within, Kubernetes, right? Sometimes you'll have cases where multiple pods might share the same service account, right, in a namespace, or you have multiple services, running on a single virtual machine, and that virtual machine has an identity, right? SPIRE, as well as workload identity, kind of gives you the ability to give specific, those specific cryptographic identities to the actual running processes. And so, kind of moving forward, right? So, this is this implementation, right, is leveraging the SPIFFE framework, which stands for the Secure Productionalized Identity Framework for Everyone. I'm glad I remembered that. And so, going on to more of the benefits, right, is that there's no need to pass any sort of seed tokens or secrets to these workloads in order to have those workloads actually join the SPIRE ecosystem, right? There's this really cool concept of self-attestation, right? Which is the ability, without going too far into the details, otherwise it'll become a SPIRE talk, is there's basically the ability for you to register a workload, right, based off of a select set of attributes. Those attributes being like, for example, I have a workload running in this particular, Kubernetes cluster with this name. The workload is in this namespace using this service account with this pod ID, right? And so if you have a workload that comes up that matches all of those specific attributes, SPIRE will actually handle the distribution of that identity back to that workload. And so it's really cool, in my opinion, at least. And so then you have that, that single workload identity that can be used to authenticate to a variety of different other destinations. So the other cool benefit, right, is that it is a cloud service provider and operating system agnostic, right? So if you're in both data center as well as, various cloud service providers like AWS, it's pretty straightforward to use. Again, it facilitates the principle of least privilege, and the other benefit too is that it has native integrations with some really cool services within AWS, such as Private Certificate Authority and KMS. So we talked a little bit, we have a primer, right, on workload identity and specifically SPIRE, right? So where does PKI come into it? So as you might have guessed, right, SPIRE itself can be a cryptographic authority if you're just using SPIRE on its own. So it, mints these workload identities, right? They can be in two different forms, really. One is X.509 based workload identities. The other is, JWTs that are signed, again, by the SPIRE cryptographic authority. But the other cool thing is that it can actually, like I mentioned previously, it can actually use upstream or external cryptographic authorities, right? And this is exactly what we wanted to use at StubHub, right? So we have basically a single certificate authority hierarchy that we can use for both, the workloads within the SPIRE ecosystem, but also the workloads outside the SPIRE ecosystem that just need, TLS or code signing, right? So in our specific case, right, we're using, the integration with Private Certificate Authority and KMS to sign the JWTs, and allows us, right, to have, full control over that revocation and all that good stuff. So we talked a little bit about workload identities, SPIRE, all that good stuff, how PKI comes into play. So let's talk about, kind of going back to our set of objectives, right, that we had when we're re-architecting our PKI. So we kind of broke it down into three different buckets here. One is we need our solution to be highly available and fault tolerant. Other is we obviously want to make sure it's secure. I'm a little biased though. And lastly, right, we want to make sure it's easily maintainable, right? And so from the high availability and fault tolerance perspective, like I alluded to, right, we're minting tons of certificates every day. So we want to make sure that we do not have a single point of failure. Otherwise, I would be the single point of failure in that scenario. And from the security perspective, right, we only want to ensure that trusted entities that should have access to request certificates or to conduct administrative activities against our internal PKI could. So no unauthorized access or anything like that. Our internal PKI solution that we wanted to build should be highly auditable, right? So though we can add these protections on top of all this stuff, we really want to be able to even then monitor, right? And so in addition to that, ensuring that we have proper certificate revocation. In our case, we chose, we really wanted to go with the online certificate status protocol. And then if we go down to the last section here, we want to make sure it's easily maintainable. And so we are already a big infrastructure as code shop, so we chose to use Terraform. And so ideally, if it was possible, right, we really wanted to leverage our infrastructure deployment pipeline in order to deploy our internal PKI solution. And that's assuming, right, we didn't have to handle any key material and have the key material sitting in a state file for Terraform. So, right, those are our objectives. What are the constraints that we were under, right? And so, at StubHub, we believe, and it actually works out pretty well, is lean, talent-dense teams, right? So those teams are responsible for many things, right? So we wanted to make sure that we had low maintenance requirements in the solution that we chose to build, right? Security engineering at StubHub owns and operates and has its hands in a lot of different foundational kind of constructs within the platform. Cloud account architecture, identity and access management, edge security, PKI, SPIRE, all that good stuff. And so, we don't have a dedicated team just to, maintain our internal PKI. And so lastly, right, obviously we want to become more secure, and have a more robust PKI architecture. But in addition to that, we want to make sure that we weren't, throwing money out the window, right? So we wanted to be cost conscious, right, while we were actually, improving our internal PKI architecture. So this leads us to the fun stuff, which is the solution, right? So now I know you guys might not believe me, but we did actually end up choosing AWS Private Certificate Authority. So we broke that out into, again, the three different objectives here and kind of why we end up choosing AWS Private Certificate Authority. So like we covered earlier, right, it is regional, it is highly available within a region, right? And we could also do, cross-region high availability, right, or having a point of presence. Oh, it is? Oh, okay. We also wanted a cross-region points of presence, right, with a single root certificate authority, which we could indeed do using this, using the AWS Private Certificate Authority. And so, in addition to that, right, we didn't want to have to, plan for high availability when it came to generating key material from a hardware security module or, OCSP infrastructure and all that good stuff. So, next we'll talk about, one of the reasons why we chose it from a security perspective. Right, we did want to have a separation between identities, right, for who could actually request certificates versus who can conduct administrative activities. And so being able to leverage AWS Identity and Access Management for that, as well as service control policies and all that good stuff, we were able to kind of get to the kind of defense in depth architecture from an identity perspective that we wanted to. Last but not least, right, with this security section is that we wanted to ensure that everything was highly auditable, right? So the good news is that with AWS Private Certificate Authority is that all actions, both administrative and operational, are logged into AWS CloudTrail. And so considering we were already, aggregating all those logs, it was, again, pretty easy sell on that front. And then so if we go down here to the ease of maintenance, right? We did want a simple way to share those certificate authorities across a number of accounts, right? So given that we're moving to, a cloud account architecture where new accounts are coming up and down, every day it seems like, if we're able to share our private certificate authorities in a way that, ensures that we don't have to drop an actual instance in every single account, and we can do so in a dynamic fashion, right? That would obviously be, great. And so we're taking advantage of using the AWS Resource Access Manager, sharing the private certificate authorities out based off of organizational unit ID with their appropriate environment. So as we'll get to in a second, we're only sharing the production certificate authority with the production AWS accounts based off of organizational units that we have in our org management account. So yeah, we wanted to take advantage of the native integrations with AWS services, right? So using things like AWS Certificate Manager to handle the the renewals, right? And having the ease of use for our developers to actually apply those certificates to AWS resources that we already plan on using, such as load balancing, CloudFront, API gateways. Most importantly, not having to have them handle that key material, right? So here is a reference architecture, an obfuscated reference architecture, what we end up building. So as I kind of alluded to, right, we chose to kind of have two different CA hierarchies, right? One of which was for production workloads, and the other was for non-production, right? And so though we do have more than just two environments, from our perspective, it did make sense to not overly complicate our certificate authority hierarchy, given the needs of our customers as well as our internal platform teams. And so over here to the right, we did put our root certificate authorities into their own AWS account. In this case, it's a PKI account. And then from there, we actually shared using AWS Resource Access Manager, we actually shared the root certificate authorities to our security engineering AWS account. And so the reason why we did that is because we wanted to ensure that we could actually have our subordinate CAs, or in this case, they're both subordinate and issuing at the same time, CAs be able to actually be signed by the respective root certificate authorities. And so in addition to that, we did want regional points of presence, right? So here you can see that we have two different regions, right? US East 1 and US West 2. And each of those regions, right, within the security engineering account have, their respective environment, right? So if you see here, US East 1, production, US East 1, non-production, right? And same thing with US West 2. After that, we chose to share those specific certificate authorities out to our organizational units, right, using Resource Access Manager. And now we have a point of presence both from a regional perspective as well as in a cloud account perspective. And so those intermediate/issuing certificate authorities can then be used to mint our end entity certificates as well as sign the individual SPIRE local certificate authorities that are used for the workload identity solution. So I think it's also kind of cool, as myself being someone who likes to attend these talks, right, I'm always curious on how they actually ended up deploying it. So like I mentioned, right, we're a big infrastructure as code Terraform shop. And so over here to the left, right, we're actually using the standardized infrastructure as code deployment pipeline. And then from there, we actually created some bespoke Terraform modules that kind of combine, the private certificate authority, the resource access manager, the CA certificates and the associated permissions that go along with them within that module. And then based off of the role in which the certificate authority plays, right? So that's not to overload the term from an IAM role, but like whether it's root or subordinate, the module is actually making the choice to, associate the proper permissions and share those certificate authorities out to the appropriate accounts. And so I think it's also worth noting, right, as a part of having, a robust defense in depth strategy, we also leveraged AWS organization service control policies to prevent modifications to, the certificate authorities themselves, right? So ensuring that they, either can or can't be disabled. So those are, actions that are completely unavailable from a service control policy perspective in those AWS accounts. Also want to make sure that, people are not allowed to create new certificate authorities, right, and have those signed. Same thing goes with, modifying the resource access manager resource policies, or the shares themselves, right? And so we kind of use that from, ideally like I was mentioning, the defense in depth strategy. So then lastly, right, given our journey and how we moved into AWS and how, our objectives and workload identity and all that good stuff, and how we end up building it, what were the lessons learned, right? So kind of got three, main points to leave you with on this particular section. First one is, build your internal PKI architecture in a way that respects your organization's needs, but is not overly complex, right? So, you don't want to have, a complex hierarchy where you end up, it takes more care and feeding to take care of and manage, as well as, cost, have basically cost additional dollars, right, where you're not getting the return on investment. So next, right, you want to ensure that, and this is actually an interesting point with any PKI, whether it's on AWS or not, you want to ensure that you have a very robust configuration management process, because as you're building an internal PKI, you need to basically install those CA certificates into your client trust stores, right? And so there's a couple different ways you can do it on AWS specifically, right? You can use AWS SSM, right? Or you can actually, in addition to that, right, you could also create, golden images from, an AMI or a container image perspective. And as a part of the bootstrapping process, you install those CA certificates in those trust stores. So, but either way, definitely have, you should always have a good process for managing configurations. And so lastly, and this is kind of one that's maybe not super obvious, but in my experiences, it's great to have, a deliberate generational naming convention, right? So as those CA certificates end up expiring, right, and maybe you won't be there at that time where they end up expiring, right? Because it's 25 years or 15 or longer amounts of time. But it'll definitely help out those engineers, later on. Is that when you're kind of swapping those certificate authorities, you might need to have two up at the same time, right? To organically move over to your refresh certificate authority. And so having the proper generational naming convention lets you easily be able to, understand what the structure is, and when you're moving from the soon expiring certificate authority hierarchy to the new one. So, yeah. Alrighty. So I'm going to pass it back to Zach, and he'll talk about connectors.
Thanks, Tony. So, Tony's talked about how StubHub had these requirements for a PKI. They do code signing, have mutual TLS between services in Kubernetes, like a service mesh. These are some pretty common use cases. You also mentioned like terminating TLS on an ALB. I would say those are, excuse me, some of the most common use cases we see from customers, but there are others, right? There are Active Directory certificate services for, when a Windows laptop, for example, in your organization joins the domain, you got to get certs to authenticate to some internal site or something like that, right? You might have iPhones or Mac laptops, and you need support for SCEP, or Simple Certificate Enrollment Protocol. And a couple of years ago, these were use cases that customers would come to us and say, hey, look, like Private CA looks great. I want to be able to not have to manage my own PKI on-prem, but I have these use cases. I have Windows stuff. I have SCEP and these kind of like mobile device management type use cases. And so these are areas where we, the vision for the service is to eventually be a kind of enterprise scale PKI that can serve all your use cases for certificates, right? And the way we're getting there is through building these connectors. And so some of these connectors, the ones I'll talk about are Active Directory, the connector for Active Directory, the connector for SCEP, and the Kubernetes connector. And so again, these are really mainly to facilitate those use cases where like just making an API call to get a cert or using ACM to get a cert is not going to work, right? Like if you're talking about a Windows domain or a domain joined device that joins the domain, they don't know how to automatically make an API call to Private CA and get a cert back, right? So let's look at, for example, connector for Active Directory for that use case. You might use certificates to secure your communications with secure LDAP, to enroll users and machines for like if you have to get access to like your intranet site or I don't know, HR, payroll type application, all like internal type applications that aren't for your public customers or public facing, but are for internal folks. You might also like use it to encrypt email, to code sign, to do any of these things, right? So we built this connector to basically kind of replicate the experience that you're used to doing this on-prem or with traditional ADCS. With how this is going to work, kind of the data flow is, or the process flow is that the domain joined object, say it's like a Windows laptop, again, corporate laptop, comes up, joins the domain. It's going to get group policy object that tells it, here's your auto enrollment server. In kind of the traditional Windows world, that would probably be like a Windows CA, maybe you run on-prem. In our case, it would be this connector. You build this serverless connector. It lives in your AWS account. You don't have to, again, manage the servers or do anything. There's no additional cost for this connector. You build that, and then you make a connection to your Active Directory environment. That can be in AWS Managed AD, or that can be AD, your Active Directory on-prem. If it's on-prem, there's a similar connector from AWS Directory Service called the AD connector. So there's the Active Directory connector, and this is called the connector for Active Directory. Not to be confused, I don't make the names. But this connector for AD is basically, again, kind of acts as that enrollment server and kind of just almost translates those requests to an API call to private CA to get the cert. So like what happens is, again, Windows laptop comes up, gets group policy, talks to its auto enrollment server, in this case the connector, and we'll provide back a list of templates. Hey, you're supposed to get machine authentication and TLS and code signing, for example. And then so that device will get that information back, and then it will create CSRs and go, send those to the connector, and it will get those certs from private CA and distribute them back to the device. The important part to remember, though, is that's all totally transparent to the user. So they don't see anything other than their Windows laptop coming up, and in the background they get certs and they can authenticate. And that is the same, again, as ADCS. Like it's going to be for your Windows users and probably for your Windows administrators largely, pretty much no change. So I think that's a nice benefit, because now you don't have to manage the servers like the Windows CA stuff. You don't have to manage any hardware security modules if you have those, but you still kind of have the same experience for your users. It's like a transparent change to them. Similarly, the connector for Kubernetes, Tony talked about their use case for Kubernetes and SPIFFE. But one way to issue certificates to Kubernetes devices, or clusters for that matter, would be to use Cert Manager. And Cert Manager is a native Kubernetes. Actually, is anybody familiar with Cert Manager already? Kubernetes? Okay, decent amount of people. Yeah, so it's a built-in utility that lets you kind of deploy services the same way you're used to in Kubernetes. Create like a YAML deployment file that says, here's what my CAs are and where to find them, here's the templates and things like that, right? So you can create this service using Cert Manager that will allow you to get certificates from private CA. We have built this plugin called we just call it kind of like a provider plugin for AWS Private CA. And so that will let you use Cert Manager like you're used to if you already use it, but get the certificates from private CA is effectively the change. And it has some nice features too that are really more of a Cert Manager thing, but it allows you to, for example, specify here's like multiple CAs, so that if one is, there's some type of outage or something's going on where you can't reach the API endpoint in US East 1, for example, you can tell it, hey, here's another CA in US East 2, or US West 2, I think, like in Tony's example from their architecture. So you can use this Cert Manager and this plugin to basically make it easier to get certificates to your Kubernetes clusters using private CA. And then lastly, the connector for SCEP, kind of similar to the Active Directory use case, but generally, like when we released the connector for AD, many customers were like, hey, this is really cool, but I have iPhones and I have a Mac laptop. My design team uses Macs or something, right? And they still need to get certificates. And so I can't get rid of my on-prem PKI because I have these other use cases, right? Like I still need to maintain both. Why would I do that? And so that's why we again are trying to build these connectors to facilitate all these different use cases. And so for those customers that were like, great, I'm going to use this connector for AD, but now I still need Mac laptops and things like that, we built the connector for SCEP. And again, what this does is integrates with like common MDM solutions, things like Microsoft Intune or Jamf Pro, that you can use to register your mobile devices to this MDM. And then it'll facilitate things like, have a device profile. It does more than just certs, but one of the things it can do is help you issue certs to those devices. And so with this connector for SCEP, it just kind of lets you use this single CA for your enterprise, fills those use cases for those kind of niche, those niche type of devices that maybe you have a few of, but you still need to maintain some ability to issue certificates to them. And similar to AD, the connector for AD, it should be a pretty seamless transition in terms of like the experience of your users and your administrators. Because again, you're just building or creating this connector, which again is no additional cost. You don't have to manage anything there. You just have to configure the connector and the permissions associated with it. And then register those mobile devices with your chosen MDM. So there are multiple types of connectors for SCEP. One is like, we call it the generic connector, and that can be used with Jamf Pro or any other MDM. And then there's also one specific for MS Intune, Microsoft Intune, and has a little bit more integration with some of their features that they have. So you configure these connectors, and again, like you would already have registered those mobile devices with the MDM, and then that MDM knows, hey, I can get my certificates via this connector from private CA on the back end. So, you know, again, not to be a broken record here, but like the benefit is you're getting certificates from private CA, not having to manage the CAs, and your user's experience doesn't really change at all. They just pull up their phone and they should have certs, transparent to them. Okay, so we talked about the connectors. A lot of these best practices we've kind of already covered, but I do want to at least go through some of these and make sure, you know, I cover off on a lot of these, because I think, you know, for example, like documenting CA structure and policies sounds obvious, but it is something that's important, because you may have, like Tony said, 25, 50 years from now, someone's trying to go in and like replace your root CA or replace your intermediate CA, and the person that built it doesn't work there. Not to be morbid, but maybe isn't even around anymore. And so, you know, you want to have all this documented and understand, like, what are my branches of my hierarchy? What are the validity periods? Things like that. Like, document all that stuff so that you have it. Secondly, you know, define those CA validity periods. I take a fairly strong perspective on this. Like, you know, at least in my, you know, me personally, Zach, not necessarily AWS, I would say make those validity periods long, right? Because especially with private CA, the CA certificate private keys are kept in FIPS 140-2 level 3 HSMs. They cannot leave the service. So key compromise, while I don't know if I want to say is impossible, it's incredibly impractical. And so I don't think it's something where you need a really, really short validity period, and there are benefits to having longer ones, right? Like if you think about, I mentioned Amazon Trust Services. A lot of our root CAs have like a 150-year validity period. And again, the reason for that is it's difficult to go through the process of updating your client trust stores to have this new root CA, because like Tony alluded to, you have to have the root CA cert in the trust store or the client won't trust that cert. And so public certs, you know, Amazon Trust Services certs, every modern browser and OS kind of automatically has that Amazon root cert in there. But a private cert, you're not going to have that. So, you know, define those validity periods and make sure that, especially for the root CAs, there are longer validity periods, so you give yourself a lot less trouble, a lot less kind of burden of going through that process. Another thing about, you know, Tony mentioned keeping it simple and keeping those hierarchies simple. Similar to the discussion around documentation, you want to make sure the hierarchy is simple because, like Tony mentioned, it's going to reduce your costs because, you know, at least with private CA, you pay $400 per CA, but also, you know, makes it easier to understand, makes it easier to do governance around it. Some customers will have many branches of the CA hierarchy, and there are use cases where that makes sense, right? Like if you want to separate manufacturing stuff from your corporate stuff. And in that case, you might even have two separate hierarchies entirely. But there are reasons to have, you know, these more complex CA structures, but I would say for most customers, keep it simple. You're going to make your life a lot easier. Keep the root CA in a dedicated account. So like Tony showed in StubHub's architecture, you know, they have their root CAs in a PKI account that, you know, has very limited access. It's very scoped down to make sure, you know, you mentioned some of those SCPs that are in place to make sure people can't re-enable root CAs or create a new CA in that account. And so, you know, keeping it in a dedicated account and really locking down that account is super important because that root CA is, again, like kind of the root of your trust or your top of your chain of trust. This one's really taken care of you by private CA, but you shouldn't ever issue a cert that lives longer than the CA that issued it, right? Because it's going to cause problems with the trust chain. But private CA, for example, won't let you do that. So like if you specify, hey, issue me a 13-month cert for a CA that's only going to live another 6 months, it just access denied. It won't let you do that. But it's just good to keep in mind in general for PKI. And then use RAM to share CAs across accounts. Really, it's a cost thing primarily, but also governance a little bit, right? Because you have, like in Tony's example, you have all your CAs in like a central account and you've restricted access to that account. Well, now some random app developer can't go and accidentally delete that CA or, you know, make some configuration change to it. You can kind of have the account boundary in AWS is a bit sacred, and so you can you know, segment your workloads like that and have your PKI in a central account and then just share it out to other developer accounts, and they can still issue certs and do whatever they need to do, but they can't manage those CAs and you reduce costs. The only don't I have, though there are probably others, but the biggest one is don't issue identity certs from the root CA. There may be very, very niche use cases where you should do this, but in most cases, the vast majority of cases, do not issue identity certs from the root CA. And I think really the only thing I want to wrap up with is a couple of key takeaways. You know, what are the two services we talked about before? ACM, private CA. Just to recap, ACM is TLS certs only, 13-month validity. They can be public or private. and you want to use this for integrated resources like ALB and API Gateway. Private CA, you can issue any type of private cert, no public certs. And you can use this for lots of use cases, right? Mutual TLS, code signing, email encryption, machine authentication. Really, you can customize the template to be whatever you want with private CA, including validity periods. You can make it live for 90 days, 7 days, 10 years, whatever you'd like to do based on your use cases. And then I think the most important takeaways I'd take away from this session is some of the things Tony talked about, those lessons learned. I talk about this stuff all the time, but Tony actually built it, so he has some really good lessons learned there. Namely, keep it simple with the PKI. Think about how you're going to do configuration management. This is good for everything, not just PKI, but getting those root CA certs out to your devices is super important. So if you ever need to switch out a root CA or something like that, it's nice to have a very automated process for deploying those changes to a trust store, right? And like Tony mentioned, you have things like AMIs and container images that you can use to do this. At Amazon, we also have some internal code repositories we provide to our developers to say, hey, here's a trust store for your system that you can use. So that's another way to do it. And so, just in general, robust configuration management is going to be super helpful. And then lastly, use the generational naming conventions, because like Tony mentioned, you might have a case where, again, say it's 50 years from now, you don't even work here anymore. Someone's trying to figure out, okay, I want to replace this issuing CA that's G1. What you're going to want to likely do is create a new issuing CA, name it Generation 2, and then you're going to start issuing everything new, all new certificates from the new Generation 2 CA. Keep the Generation 1 CA running until all the certificates it issued have naturally expired, and then you can remove it. So say you have 50 certs left and they expire in 6 months, you would keep that additional one running for about 6 months, issue everything from the new one, and then just remove the old one when it naturally expires. You can also force revoke and just push new certificates to everything, but I find it's a little bit better to keep both running and then just kind of get rid of the other when they naturally expire. But again, you want that generational naming convention so you don't accidentally delete the new CA or things like that. You want to keep it very clear to everyone, even if they weren't there when it was built, how this all works, how it's all set up. Okay. And that is it. I really appreciate your time. Please take the survey and tell us what we did well and what we can do better. And find us out in the hall if you have any questions. Tony actually built this stuff, like I said, so hit him with all the hard questions. But yeah, really appreciate your time, and thanks again.